I'm going to talk about porous materials, which is kind of related to the previous presentation, and I'm also going to talk about microplastic material models. So there's not so many formulas in my presentation, so I tried to illustrate you some basic observations that we made in a very recent study together with Samuel Fritzen. First, some motivation. We're looking here at metal plasticity, and in metal plasticity for ductile materials, the void growth, coalescence, and nucleation are the major effects that are driving the ductile deformation and also the ductile failure of materials. So it's very important to thoroughly understand the effects of these ductile deformation processes. So this is one of the main ingredients, and the second one is that you observe scale effects in metal plasticity, which are often dominated, for example, due to size effects induced by the grain size that you observe in the polycrystalline microstructure of the material. So we would like to combine the two effects, so we would like to look at porous materials possibly exhibiting size effects. And therefore, we petition a presentation as follows. We first go briefly into introduction and modeling. So I'd like to briefly review some results for incompressible metal plasticity of von Mises type, where we'll also see curves related to the Gerson model, but also to numerical results related to porous metal plasticity without size effect, and then try to do numerical limit analysis for materials which involve a size effect, and there are some very nice observations related to this. So in brief, what we're looking at is we're looking at microstructures with pores. So the pores are drawn in green here, and we assume that the matrix material surrounding the pores is made of a material that exhibits a constant yield stress, and the matrix is assumed to be plastically incompressible. So that means that we're looking here at von Mises yield criterion without hardening, and we're interested in varying porosities. So from small porosities as low as 0.1%, for example, up to 30%, which is very close to the percolation limit that we have for the microstructures we're interested in, which exhibit a Boolean model of hard spheres. So that means that we're looking at microstructures where the pores are all of equal size. They are randomly isotropically distributed, but they do not overlap. Then going back to the seminal work of Gerson, like in the late 70s, that many of you are probably aware of, he looked at a hollow sphere model where the inner part is basically the pore, and then if you look at a loading of this very particular microstructure, you can relate the yield stress that this pore can undergo to the applied pressure P and to the porosity F. So this relation is known for long, and what we were interested in a study that we performed in 2010 is the Gerson's prediction really something that is reliable? So is this a good approximation for realistic microstructures exhibiting a large variation of the porosity? And therefore we performed a computational study. So what we were doing actually is we were trying to vary porosity between 0.1 and 30%, as mentioned before. We created artificial microstructures, and we made sure that these microstructures are in fact representative for the class of materials that we're interested in. So we checked that the microstructures were isotropic, that the size of the RVE is sufficient in order that the computational findings are also representative. So, for example, the artificial microstructure may not be too small in the sense that they're not sufficient. There's not a sufficient number of pores. So for example, for the higher porosities, you need at least 30, 40, 50 pores in order to have results that do not depend too much on the pore placement, given the constraint that the microstructure is made of a Boolean model of hard spheres that is isotropic, for example. So we also did gather some statistical information, so we redid the calculation using small variations in the microstructure by changing the pore placement, and then took ensemble averages and verified that the results did not vary too much, for example, just in order to make sure that the size of the RVE is adequate for this problem class. And we looked also at the formation of slip bands, so this produces these very nice images where you have a localization of the plastic deformation due to the non-existence of hardening stresses in this plastic material. In total, this leads to like 2,000 nonlinear finite element computations, so this is very costly, and we would like to find an effective material model that is based on these 2,000 points. So what we did is we tried to exploit these results from numerical limit analysis to do computer-assisted model identification. So here you see most of these computational findings. For the smaller porosities, we have here the hydrostatic stress and the macroscopic hydrostatic stress and the macroscopic von Mises stress, and you see neatly that the point where pure applied pressure leads to a pore growth is very, very strongly depending on the porosity, but also the von Mises stress depends on the porosity of the microstructure. And if you compare that, especially for the higher pore volume fraction, to existing models from the literature, you find that qualitatively you have some kind of accordance, but quantitatively these curves are far off, especially for the very high pore volume fractions. So we tried to find a model that is simple, yet able to replicate all these computational points with a low number of material parameters. And this is why we came up with the adjusted Gerson-Twergert-Needleman model, where the Gerson-Twergert-Needleman model is a rather simple, straightforward extension of the Gerson model, in the sense that you replace the porosity by some sort of a effective porosity. This introduces 3 additional parameters, Q1, Q2, and Q3, and you can make these parameters depend on the porosity, which is what we did, and this provided us with this model. It only has 3 additional parameters, and the dependence is straightforward and produces these very nice results where you can see that a rather simple model can replicate lots of computational findings. So we were now interested in answering the question, is it possible for materials exhibiting length scale effects related to like gradient type plasticity theories, is it possible to perform numerical limit analysis and maybe come up with a model that can also capture size effects in porous metal plasticity? So therefore, we're looking at a strain gradient, at a micromorphic plasticity model which mimics strain gradient plasticity, going back to Ifantis and some works of Samuel Forrest also. And what we do is we introduce a scalar microplastic variable chi, which is can be interpreted in a certain sense as a measure for the accumulated plastic strain that is found in the material. And then we try to enforce that the accumulated plastic strain Q, the exact accumulated plastic strain Q, is more or less equivalent to this microplastic variable using some kind of a penalty formulation where we penalize the deviation between the hardening variable and the microplastic variable using this parameter h chi. And then also in the free energy you have another contribution which accounts for the gradient. So basically this term here involving a length scale LC accounts for a penalization of the gradient of the microplastic variable, whereas this part here penalizes deviations from the microplastic variable to the hardening variable. Then you can come up with classical constitutive equations derived, for example, by means of virtual power and balance equations, so I'm not going to detail that. But in total, this is basically a strain gradient plasticity model if you enforce that Q and chi are more or less equivalent. So here's an example. We, in order also to verify the numerical implementation, in a recent work, Samuel investigated this specimen here undergoing a shear deformation, where you have an elastoplastic and an elastic phase, and you have this microplastic material model in both phases, where the plastic strain is 0 here, but the microplastic variable may be non-zero even in the elastic phase, as we've learned already 2 days ago. So here you see the yield stress of the material, and at the bottom you see the equivalent plastic strain. Here on top you see the norm of the gradient of the microplastic variable, and on the bottom you see the microplastic variable. So these two should coincide, but you see that this hard interface for the accumulated plastic strain is kind of diffuse in this model, which is due to the fact that the microplastic variable also propagates into the elastic phase. So these results are all in accordance with analytical findings that we have for this model. So this made us confident that the implementation is also working properly, so we tried to move on. But before doing that, we try to observe a bit what is the role of the different parameters. So first of all, the yield stress of the material depends now on the mismatch of the microplastic variable and the hardening variable, and on this parameter h chi. The higher h chi, the higher the influence of this mismatch on the yield stress of the material is. Second, if you look at variations of this characteristic length LC, you find that if you increase LC considerably, the microplastic variable chi gets significantly more homogeneous. And this also means, since the accumulated plastic strain is not as homogeneous, that the influence on the yield stress via this first observation gets more pronounced. So in total, there is a significant influence of this factor LC, and now we want to learn how this transfers to the porous plasticity. First, if you send LC to 0, we recover the von Mises plasticity model, and if we send LC to infinity, we get a homogeneous microplastic variable, and then a very high penalization of this mismatch, and a largely varying yield stress, although the microscopic yield stress is assumed to be constant for the material model, which is interesting. We examined a very simplistic microstructure at first, which involves only a single pore at 6.54% volume fraction. We applied periodic boundary conditions, used a finite element discretization using quadratic shape functions here, and applied shear to this unit cell, and we observed basically the macroscopic shear stress, sigma 1, 2. Material parameters were kind of arbitrary, and what we did is now we varied the length, this parameter LC, to be in a range between like 1,000 of the length of the cube edge to 0.5 of the cube edge. And we also performed the mesh density study just in order to make sure that our discretization is fine enough to capture all the effects that the microplastic model has, and to capture effects due to the plastic deformation of the material. So we found that discretization level H3 with like 150,000 degrees of freedom is more or less sufficient in order to capture all the main effects of the global response. But then we looked also at the local field. So this here is, for example, the accumulated plastic strain. This was the discretization level that was largely sufficient when just considering effective quantities, and we wanted to make sure that we capture all effects, so we picked one discretization that was even finer, involving now approximately 450,000 or 60,000 degrees of freedom. So a rather fine discretization was used, and then we varied LC in a broad range, and here are only selected curves. So the red curve here on the bottom is the one with the smallest characteristic length scale, and you see that you have an almost constant response over the entire range of applied shear strain, whereas if you increase this characteristic length, for example the blue curve immediately jumps up here, and it's not so clear to see that. Here is a black line which is just the yield stress times the matrix volume fraction. So this is kind of the upper bound that is predicted by some kind of a Voigt or Taylor estimate for this material. So you cannot go basically beyond this limit. This is basically a homogeneous stress distribution within the matrix. So it's very interesting that if you increase the length, the characteristic length, you immediately jump to this upper bound. And if you have intermediate values, you have something in between. Now we wanted to compare this also to the von Mises model, so we traced that. So this is basically LC equal to 0, and you see that for the small length scale, you're close to the von Mises model, but as the deformation continues, you're moving away. And this is due to some kind of apparent hardening modulus that is due to the size effect that is induced by this length scale parameter LC. And we're going to investigate that a bit further. So we tried to interpret again the effect of LC, and what we found is basically that if LC increases, this leads to an increasing penalization of the norm of the gradient of the microplastic variable. And this increasing norm, penalization of the norm, induces that the plastic strain gets increasingly homogeneous, and thereby induces also a more or less homogeneous plastic strain state. And this homogeneous plastic strain state then leads to this almost to this constant stress state within the matrix material, where you reach actually the Voigt bound. So independent of the choice of the parameter LC, if you apply the loading like sufficiently long, you always fall to this upper limit. So this precludes these gradient materials from numerical limit analysis a priori. Because as soon as LC is non-zero, you will always find asymptotically this upper Voigt type bound, and you cannot prevent that. But what is interesting is that the transition time to attain this asymptotic stress state gets significantly influenced by the parameter LC. So there is a subsequent study required because you will never attain in practice the asymptotic state. So limit analysis is probably not the proper tool for these gradient type materials. Here are also some local field distributions. Here's the hardening variable. We have one on the left-hand side, a rather big value for the characteristic length, on the right-hand side a rather small value. And you see here, you have to consider that here you have a rather confined scale for the hardening variable in comparison to this here. You see that the hardening variable is more heterogeneous in this example, but this is particularly true if you look at the microplastic variable, which is almost equivalent in these two cases here, but here it's more or less constant. If you look at these values, there's almost no variation between the blue and the red. So you have a homogeneous microplastic variable on the left-hand side. So this is one of the effects that you observe locally within the voided material. Here's yet another example. We investigated also the formation of slip bands in these materials. Again, a rather big value for LC and a rather small value also here. This goes up to like 7.5% of equivalent plastic strain. Here it's just 2%. You see it's almost homogeneous at the end. And maybe I can run that again. You see here a very pronounced localization of the plastic slip, which is much more pronounced than in this case here. So the parameter LC significantly contributes to the width of the slip bands observed in the simulations. I was talking about this apparent hardening modulus, and we evaluated that numerically based on the observed data. So we took just like a finite difference scheme, so to say, with some smoothing to find this apparent hardening modulus. And what is very interesting is that this hardening modulus kind of keeps saturating towards a lower limit, and for these higher values of LC is more or less independent in this strain range observed here. And here is a zoom in to the stress space. So you have here the equivalent stress. I did cut off like the elastic part more or less, and some part of the transition regime. And you see here for a small characteristic length you still have some kind of like apparent hardening, whereas the apparent hardening is already saturated for the higher values of LC. So subsequent studies will have to tell us how can we predict this apparent hardening as a function of the applied load and as a function of this characteristic length LC. And this brings me basically to the conclusions. We have used a rather simple microplastic model mimicking gradient plasticity in order to investigate the effect of the length scale parameter LC in voided materials using some kind of numerical limit analysis. We found that numerical limit analysis is probably not the proper tool, so you have to really consider the transient response undergoing this nonlinear plastic deformation. And we found that if you increase this length scale parameter, you see so LC is small here and big here, and this is basically at the same applied load, and you see that this also has a very significant influence on the deformation field. And here we trace the norm of the gradient of the microplastic variable. So this basically bounds the plastic slip bands very neatly, and you see that here you have a homogeneous plastic deformation. So with that, I'd like to thank you for your patience, and we'll be willing to answer your questions. Thank you.
Is your three-dimensional finite element?
Yeah, sure. This is a 3D finite element simulation here.
And which not that degrees of freedom you choose?
It's just the 3 displacements and the microplastic variable. And it's all P2 elements.
Okay.
are using this model where you have the second ingredient in the internal life.
Yes.
But in the internal energy, you use, it seems that the internal energy depends on the ingredient you use. There is some reason for this.
Yes, the reason is that the plastic strain is not really a state variable, but the gradient of it can be considered internal.
Yeah.
State. Yeah.
Exactly.
Yes.
Is this work preliminary to actually be extended to a random microstructure or?
Well, yeah, it can be extended to random microstructures by just using a different finite element mesh. But this was just a very preliminary work, so to say, and we just wanted to see what is the effect. And what we found was interesting because we could have used artificial random microstructures at will. But we found using the simplistic microstructure that this may not even be useful. So first we have to think of a proper way of analyzing the effect of LC in this loading history. And then we can come up with artificial microstructures involving multiple pores, for example. Okay, thank you.